Mathematics feels like the one place where everything should make sense. Every equation follows rules. Every problem has an answer. And if we just work hard enough, we should be able to prove every truth that exists. But in 1931, a young logician named Kurt Gödel revealed something astonishing. Even the most perfect system of rules will always leave some truths out. In this video, we're going to break down Gödel's incompleteness theorem in the clearest way possible. No heavy logic, no intimidating math, just the simple idea that changed how we understand knowledge itself. Most people think of mathematics as the most perfect thing humans have ever built. Clean, precise, certain. A universe where every statement is either true or false, and every truth can eventually be proven, if you're smart enough or patient enough. But in 1931, a quiet 25-year-old logician named Kurt Gödel proved something shocking: that dream is impossible. No matter how perfect you make a mathematical system, it will always contain true statements that the system can never prove. In other words, truth is bigger than proof. And that idea shook mathematics philosophy logic and even modern computer science to its core. But to understand Gödel's incompleteness theorem, we're not going to use equations or symbolic logic. We're going to explain it through simple ideas anyone can understand. Because the heart of Gödel's discovery is not complicated. It's profound. Let's start with the world Gödel was born into. Back in the early 1900s, many mathematicians believed they were close to completing the final version of mathematics. Led by the legendary David Hilbert, they dreamed of building a perfect system of rules that could prove every mathematical truth. Hilbert wanted two things. First, consistency. The system should never contradict itself. Second, completeness. The system should be able to prove every true statement. Imagine a giant machine that could, in principle, settle any math problem in existence. That was Hilbert's dream, a world where mathematics was a sealed, flawless structure with no gaps. Gödel then arrived and quietly destroyed that dream. So what exactly did Gödel prove? He proved something almost poetic. Any logical system strong enough to include basic arithmetic can never be both complete and consistent. There will always be true statements that the system can't prove. No matter how hard you try, the system will always leave something out. This sounds abstract, so let's make it simple. Gödel's key idea was a brilliant trick self-reference, a statement that talks about itself. But instead of using messy sentences like "this sentence is false," Gödel encoded everything into arithmetic. He turned statements into numbers, proofs into numbers, and logical rules into numbers. This let him craft a mathematical statement that essentially said, this statement cannot be proven within this system. Now let's think about this slowly. If the system could prove that statement, then the statement would be false because it claims it cannot be proven. That would create a contradiction. But if the system cannot prove the statement, then the statement is true because what it claims is happening. It's true, but unprovable. In both cases, the system fails. Either it proves a false statement, or it cannot prove a true one. And since systems are supposed to avoid contradictions, the second option must be true. There is a true statement, absolutely logically true, that the system cannot prove. No matter how hard you try to fix the system, expand it, or strengthen it, this problem reappears. Add new rules and Gödel's method will create new, unprovable truths. The incompleteness is permanent. So Gödel didn't show that math is broken. He showed that math is too big to ever fit inside any single system. To understand how surprising this was, let's use a simple analogy. Imagine mathematics is a giant library. Every book is a mathematical truth. Hilbert wanted to create a perfect catalog, a complete list of all the books with rules for identifying every true statement. Gödel then writes a new book whose title is, "This book is not in the catalog." If the catalog includes it, the catalog becomes wrong. If the catalog excludes it, the catalog becomes incomplete. The library is bigger than the catalog. Always. Or imagine you're trying to write a perfect handbook that contains every possible rule about numbers. Gödel's method allows you to create a new rule that says, this rule cannot be found in this handbook. If it appears in the handbook contradicts itself. If it doesn't appear, the handbook is incomplete. This wasn't a trick. It was a structural limit of all formal systems. Gödel didn't destroy mathematics. He revealed its depth. And it gets even deeper. Gödel didn't just prove one theorem, he proved two. His second incompleteness theorem says, a system strong enough to describe arithmetic cannot prove its own consistency. In plain language, no system can guarantee, using only its own rules, that it will never lead to contradictions. This was devastating to Hilbert's original dream. Mathematics cannot prove its own reliability from inside itself. To prove a system is consistent, you must appeal to something outside it, a stronger system. But that stronger system then faces the same problem. And so on forever. Gödel revealed an infinite ladder of systems, each capable of proving things about the one below it, but none capable of proving everything about itself. This changed everything. In mathematics, it meant there is no final ultimate system of truth. There is always more to discover, always truths that escape any particular method of proof. In philosophy, it meant that human reasoning has structural limits, not because we're flawed, but because reasoning itself has boundaries. In computer science, Gödel's ideas inspired Alan Turing to prove that some problems can never be solved by any algorithm. And modern AI research still runs into Gödel-like limits. No machine can completely analyze its own behavior using only its own rules. Gödel showed that every formal system has blind spots, truths. It cannot see statements. It cannot decide boundaries it cannot cross. And here's the twist that many people miss: Gödel didn't make mathematics weaker. He made it richer. Before Gödel, mathematicians believed that truth and proof were the same thing. If you can't prove it, maybe it isn't true. After Gödel, they understood something deeper. Truth is bigger than proof. The universe of mathematical truths is far larger than the slice we can capture through any rigid system. Gödel didn't just reveal limits. He revealed possibilities. He showed that mathematics is not a closed box. It's an open landscape, always expanding, always extending, with infinite truths, waiting beyond the reach of any single formal method. And that might be the most inspiring part of all. Gödel's incompleteness theorem doesn't say we'll never understand everything. It says there will always be more to understand. It turns mathematics from a finished monument into a living, breathing exploration. It turns the search for truth into a never-ending adventure. It turns the idea of knowledge into something dynamic rather than static. Gödel proved that even in the most logical, structured, precise domain of human thought, mystery survives. And because of him, we now know that no matter how far we go, how deep we explore, or how complete our understanding becomes, there will always be truths beyond our grasp. Not because we're limited, but because truth itself is limitless. That is Gödel's gift, a reminder that the universe of ideas is infinite and our search for understanding is never truly complete. If this explanation helped Gödel's theorem finally make sense, imagine what other deep ideas become simple once you see the story behind them. Gödel showed that truth is bigger than proof and that understanding is always an open horizon, not a closed box. If you want more videos that turn the biggest ideas in math, logic, and science into clear, engaging stories, make sure to subscribe, leave a like, and tell me what you want explained next. Thanks for watching Plain Explain, where complexity becomes clarity.